Hi guys, and welcome to today's lesson on unions and intersections, and what a joy and a pleasure it is having you watching along. Hi, I'm Darren, otherwise known as the Maths Guru. I know. Do you know so many people say to me, what, can you not spell? And I'm like, oh no, not really, I'm a maths teacher. A bit random, but welcome. Look, guys, if you haven't already, there's that little red arrow over there, that doohickey that says subscribe. You've not got a YouTube account? Sign up. It's easy and quick and really helpful if you sort of subscribe. And if not, get out there and tell your friends. And in fact, tell your friends. It'd be really, really helpful. And it makes me feel like I'm not actually just doing this in a room on my own, which if you could see at this moment in time, I'm quite literally sitting in a room on my own, talking to myself. Everywhere else, this is just insane. Here, it's educational. Bizarre. Now, obviously, what you are here for is a lesson on unions and intersections. Yes, I know, exciting stuff. And you're like, what's a union and intersection? I'm getting to that. But as is normal, let's just look at what I'm hoping to cover in this lesson. Firstly, what is a Venn diagram? Secondly, how do you draw a Venn diagram? Thirdly, what does it mean for a union? What does it mean by an intersection? And how do we use those concepts of unions and intersections to calculate probabilities and numbers of and all sorts of funky stuff? Now, again, don't worry about it if you don't understand even the language at this moment in time. It's fine. I'm going to recap a couple of things here now, as you can see. Firstly, sample space. It's important to know the sample space is effectively a complete list of outcomes from an experiment, or the possible outcomes from an experiment. So if I was, for example, to throw a die, a normal six-sided die for that matter, then I might expect my sample space to have curly brackets and the values 1, 2, 3, 4, 5, and 6. Why? Well, quite simply because those are all the outcomes that have come from a die. Notice this letter A here. Now, for some reason with probability, we use capital letters to define or to stand for particular events. And what does it mean by event? A collection of outcomes. Oh, look, I've said that one there, event. Oh, what did I say by an outcome? Well, throwing a die will have 6 outcomes. There are 6 possible things that can happen. Whoa, this is awesome. What would a trial be? Oh, well, I could stand in front of a judge and go, Your Honor, I'm not guilty of teaching mathematics badly. And I'm not. I'm trying really hard. But the point of it is, a trial is the act of performing a single experiment. So flipping a coin once is a trial. Rolling a die once is a trial. And equally likely, I think that one's fairly self-explanatory. Hopefully, when we toss a coin, there is an equal chance of getting a head and a tail. And pretty much that's true. When I roll a die, there is pretty much an equal chance of getting each of those numbers. It's not biased. That's assuming there are numbers 1 to 6. If there were 2 number 1s on there, then obviously there would be a greater chance of getting a 1. So it's not equally likely. Now, knowing that language, we can move on to this wonderful thing called a Venn diagram. Now, a Venn diagram, I have no idea who Mr. Venn was. I'm not even sure he was a person. It could have been a lady, by the way, just chill. I know. But the great thing is, drawing a Venn diagram is ridiculously simple because the first thing you draw is a rectangle. And the next thing you draw is 2 circles or 3 circles. And the number of circles depend on how many events there are. So how many different things you are doing. And I've got an example here of 2 events rolling a dice. So I suppose the best thing to do is actually draw one and sort of explain how they're drawn as I'm doing it. Right, so the first thing is a Venn diagram is always surrounded in a rectangle. And I have seen people draw just circles and go, well, that's a Venn diagram. It is not. It has to have a rectangle. It should always have an epsilon there. Now, that's a Greek letter, epsilon. I even did that backwards. You notice? Well, it's backwards to me. It's the right way for you. Now, in this situation, we then have to consider our circles. Now, normally we draw 1 circle for each event. And if we can see here, we've got 2 different events. One is throwing an even, one is throwing an odd. So we would have a circle, and generally outside we'd have an A for the even, and we'd have a circle with B for the odd. Now, at this moment in time, I'm going to draw these circles quite separate. They are not going to overlap. There is my A, there is my B. Inside each of those circles, you write all the possible outcomes that could happen. Now, because we're rolling a die, we know our sample space would be 1, 2, 3, 4, 5, and 6. We know the probability of A happening is that there is an even number, and the only even numbers that are possible are 2, 4, and 6. B is the probability of throwing an odd number, and so that is 1, 3, and 5. Now, does that cover all of my outcomes? Are all of the numbers in those circles? Well, yes, 1, 2, 3, 4, 5, 6, I can see them. And ladies and gentlemen, there is my Venn diagram. Not particularly complicated, is it? No, and I promise you it doesn't really get much more complicated because you're just drawing rectangles with circles inside them, yes? The big question you're going to ask yourself in a moment is, do those circles overlap? In this situation here, and I'm just going to say, the fact that circles do not overlap mean that my data is mutually exclusive. Ooh, we like to be exclusive. Yes, we'll have none of this more than one thing. Thank you very much. Now, in this situation, mutually exclusive means there is no overlap. That what happens in A and what happens in B are completely separate. So, for example, the probability it rains against the probability that I eat a peanut butter and jelly sandwich. Why do I always do this with food? I always get hungry doing these videos. Are they going to overlap? Does the probability of me eating a peanut butter and jelly sandwich have anything to do with, I don't know, the fact it's going to rain? No. So they're mutually exclusive. Then we move to the idea here where we got two events, A, which has the numbers 1, 2, 3, 4, 5, and 6, and B has the numbers 3, 4, 7, and 9. Now I'm going to draw it over here for a second because I'm actually going to draw it wrong first. So there's my circle, there's my epsilon. Now epsilon just stands for that rectangle is going to contain all of my possible outcomes. That's what the epsilon stands for. So here is my A, and here is my B. Now if I draw them separately, and remember I'm telling you that I'm drawing this wrong, 1, 2, 3, 4, 5, and 6, and then I've got 3, 4, 7, and 9. Now actually, when there are numbers shared between A and B, we have to draw the circles overlapped, and I'll show you why. So here is circle number 1, and here is circle number 2. Now, a really bad circle, but trying to draw this with electricity. This isn't my pen, it's electricity. It's very exciting. It's like Harry Potter's wand, but just not as quite as... Expelliarmus! No, doesn't work. Oh, let's try that one again. I could disappear. No. So, what I'm now going to do is, first things first, the overlap, those bits where the two circles cross, I'm going to write the numbers that are shared. We see that there's a 3 in both of them, so I'm going to write a 3 there, and there is a 4 in both of them, so I'm going to write a 4 there. They are the numbers that are shared. The rest of the numbers that are in A, but not in B, I'm going to write in the rest of my A circle. So I've got 1, 2, 5, and 6. And B, the numbers that are left are 7 and 9. Does that now have all of my numbers contained within those two circles? Well, I should cocoa. So again, this one here is wrong. This one here is freaking awesome with my epsilon on the top. The A and the B have all the numbers inside them. We've got the overlap. It's great. Now, the great thing is that this little bit here, this section here, is called an intersection. Now, if you go to America and you look at roads, they actually call them intersections where they meet or cross. And I think that's freaking awesome because mathematics and Americans don't normally go hand in hand. Sorry, America, I'm just joking. LOL! That's everyone cancelling their subscriptions if you're American. But the point of it, intersection means meet. So, other examples of an intersection. And I think the point about the one I'm about to draw is, again, it's subtly different. So here is my intersection. 1, 2, 3, 4, 5, 6, 7, 8. And I'm going to write 9 and 10 there. And there's A and there's B. Now, do you notice I've written numbers outside of that circle? Well, these are numbers that are actually left and not included. So, for example, we could say that event A was given by the numbers 1, 2, 3, 4, and 5. And event B was given by the numbers 4, 5, 6, 7, and 8, which makes sense because we can see all of those numbers, the interlaps or the overlaps are all there. But it may well be that my sample space, my set of numbers, notice that epsilon was actually 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Whenever numbers like the 9 and 10 are not being used in the A and B or A, B, and C if there's 3 circles, you have to write them outside of the circles, right? They're still there. They're still part of the experiment I did. They were still possible choices. They just don't fit into the circle A and B. All right. Now, again, the way we talk about maths is really, really important. Intersection has a very special symbol. And what we say is we say A, N, B. Now, that's not actually the letter N. Please don't think of that as letter N, and don't draw it like a normal N there. It doesn't have that little tail, okay? N is just basically an upside down U. So whenever you see that, it is specifically talking about this section here. the overlap, that intersection. Now, lots of people say, well, how do you remember intersection is there N? Well, because N. The second letter of intersection happens to be, I don't know, an N. So, is there anything else we need to learn? Yes, of course there is. Now, again, back to America, State of the Union discussion, all right? And I think it's the president goes and has some sort of a little bit of a rant, a bit of a talk, and it's called the State of the Union. And when you unite people, you bring everyone together. You have everyone. So, ladies and gentlemen, the union of the data is when we look at all the data joined together. So, let's draw another Venn diagram. Doop. There is event, and there is my event. A and B. Now, those circles should really be the same size. There shouldn't be any difference. 1, 2, 3, 4, 6, 7, 8. Now, if I was to list these separately, then I'd say that A was equal to 1, 2, 3, and 4. And B would be equal to 4, 6, 7, and 8. All right? Because the overlap, they've got the 4 in both of them, and B's got 6, 7, and 8 in it, and A's got 1 and 2 in it. If I want to know what the union is of this, what I'm basically saying is, do me a favour, mate, write down all the letters that appear in both A and B. So, the union of those, and I'm going to tell you that the way we express that is A, U, B. Now, anyone out there who goes, why did you find U for union? Please switch off now, give up, unsubscribe. I'm joking, don't unsubscribe, just turn off the notifications. Yes? A, U, B means write down the union of A and B. I would write down 1, 2, 3, 4, 6, 7, and 8. Now notice that I do not write 4 twice. Yeah? It's not like writing all of the elements in A and all of the elements B just side by side. It doesn't mean. It just says write down everything that you can see that falls inside that joint circles of A and B. I love this stuff. This is freaking awesome. Now, math is a huge trick, and unfortunately we use alternative notation just to try and trick you. Venn diagrams are awesome, but we can describe things in different ways, and I suppose the first thing you need to know is what a compliment is. And so I looked it up on my dictionary, and what did it say? A polite expression of praise or adoration. Well, obviously being a teacher, we get none of those. No, really, none. So, I don't know, if you fancy making a comment, maybe below. Great video, MaffsGuru. Love your work, MaffsGuru. Keep it up, MaffsGuru. I've bought you a house, MaffsGuru. Hey, that would be good. Then show the love. But sadly, compliment is not what we talk about in probability. Actually, that's misspelled. What I actually mean is compliment. C-O-M-P-L-N-E. M-E-N-T. It's always a good idea to make sure we get the E rather than the I. Again, if you want to pay me a compliment, that's awesome. Now, the complement basically means the opposite, or the chance of not something happening. And the example I give here, if we have the probability that an event A happens is 0.4, then the probability that A doesn't happen, and you notice the little line over the top, must be 0.6. So if A was the probability of it raining, so the probability of it raining is 0.2 on any one day. The probability of it not raining is given by 0.8. And notice that those two must always add up to 1. That's what the complement means. More formally, we can look at the idea that we can write this as the probability of A not happening is 1 minus the probability of A happening. It's all very exciting, and probability just restates stuff, yeah? So, what does this actually mean to anything? Well, what I'm now going to say is, here is my Venn diagram, and here is my set, and here is a circle, and here is a circle, and this is A, and this is B. Right, I'm just going to change my pen color. We can talk about various areas in different ways. So the first thing is, this little area here that I'm just shading in red is equal to, can be re-expressed as the probability of A and not B. Now you can say, hold on a moment, you did a little dash. I did, because maths is a trick. I know it can be a little line over, but you know what? Funnily enough, it can also be a dash. A dashed is equal to 1 minus the probability of A. Maths, why don't we just choose one thing? That's what I want to know. Why can't we just choose one thing and make it consistent? So, and you'll notice that does not include the overlap. It is really, really important that you realize that is the area of A and not B happening. So it's just that. In the same way as if I was to now do this shading here, this is the probability of not A and B happening. Okay, so not A and B. Cool. What do you reckon this horizontal section is called? Oh yes. Well, that's called the... Oh, hello. Let's try that again. I'm just going to make my arrow slightly bigger. That is the probability of A and B happening. Now, we already knew that. So when there's that overlap, that's that intersection. So just the horizontal bit is called the probability of A and B. And all the rest, all the stuff outside, all that blank stuff, is given by the probability of not A and not B happening, or the intersection of not A and not B. All right, so everything that isn't A and B. Getting used to that notation, having that in a summary book, remembering it is actually going to be really, really helpful. Now, moving on, we have these things called probability tables or Karnaugh maps, which are just da bomb. So I'm going to go back very quickly and draw my Venn diagram that I had just a moment ago. There's A and there's B. So we knew that this section here was given by the probability of A and not B. This here was the probability of not A and B. This intersection was the probability of A and B. And then this section here was the probability of not A and not B. Now, a probability table is just a way of expressing that same information. Oh, this table is horrible. In a table. All right, and here's how we do it. So the first things we do is we say here is A and here is not A. And here is B and here is not B. Now what we're saying is this row here contains the probability of B happening, this row here probability of B not happening, this A happening, this not A happening. So this box here, if we now think of this as N, is the idea of A and B, or A intersection B. So where's that on my graph? It just turns out that that's a little bit there. This here would be not A and B. Why? Because it's in the not A column and the B row. So not A and B, which would be this bit here. This would be A and not B, which happens to be A and not B, which is there. And this would be not A and not B, which is obviously all the stuff around here. Now, the thing to know about all of these diagrams is, the table is, that value there has always got to be 1. Why? Well, what do the probabilities always add up to? 1. Now, that's if we're dealing with probabilities. If we're dealing with numbers of, and I'll explain what I mean by that in a moment, then that value has to be the sum total of everything. But at some point, you're going to have to be able to interchange between a Venn diagram and a probability table or a Karnaugh map. So, ladies and gentlemen, let's just put this into practice now and draw some diagrams, and you'll go, okay, this is easy. Firstly, these examples are taken from the Cambridge Essential textbook, which I'm using to teach my students, and it is a fabulous resource. From a class of 30 students, right, firstly, why have they told me 30 students? Well, that's my total number of students. Okay, 12 enjoy cricket, 14 enjoy netball, and 6 enjoy both. Now, both, whenever they give you a question with both, that is giving you, in huge, flashing neon lights, the intersection. So 1, illustrate this information in a Venn diagram. All right, so here's my Venn diagram. 1, 2, 3, 4. How many different events have I got? Well, I've got 2, cricket and netball. So 2 circles. Hello, cricket, and hello, netball. So there's cricket and netball, and there's E for epsilon to say everything in there. Okay, 12 enjoy cricket. Now, what that actually means is 12 people in total enjoy cricket. And when you draw Venn diagrams, you're always interested in putting this value on first. This, how many do both? Because that's the overlap. So 6 enjoy both cricket and netball. But 12 people in total enjoy cricket. So this value here has to be 6. Why? Because in that cricket circle, there cannot be any more than 12 people. We've got 6 in the overlap, which means 6 must be just cricket alone. Likewise, 14 enjoy netball. So what do I have? 14 enjoy netball, but 6 enjoy netball and cricket. So 14 take away 6 gives me 8. And you might argue, well, that's the end. No, it isn't, because we now have to check that we've included all of my students. There might be students who don't play cricket or netball. So let's look at this. 6 plus 6 plus 8 gives me 20 Okie dokie. Well, there is obviously now 10 students that are outside of playing cricket and netball. Now, notice here I'm not putting distinct numbers. I'm not doing probabilities. I'm just saying the number of people. So now we're going to start answering the questions. State the number of students enjoy only netball. Well, now, reading off my diagram, the ones who only enjoy only netball are these ones here. And so reading off, it's just 8. Part 2. Neither cricket nor netball. So if they don't like cricket and they don't like netball, then they're falling outside of my probabilities. And that must be this number here, which is 10. Well, that was easy. What about C? So this is B. What about C? Find the probability of the student chosen at random. Now we're in probabilities. Will enjoy netball. So the probability they like netball will be the number of students who like netball divided by the total number of students. Well, how many students like netball? 8 and 6, which gives me 14 students like netball out of a total of 30, which would become 7 over 15. See how this is? This is just beautiful. Netball only. So the probability of netball only. I don't know how we're going to write that. So let's say netball only. How many people only like netball? Well, we said there were 8 out of 30, which gives me 4 out of 15. Thank you very much. Job done. Thank you very much, Mr. Venn Diagram. And part 3, both cricket and netball. Well, if you count the people who like both cricket and netball, we've already decided that that situation, probability of both, would give me 20 over 30, which is 2 on 3. Now notice how I'm writing everything with PR, PR, PR. Why? Because it's actually seriously important. All right, that was relatively easy. Sounded hard, this Venn diagram stuff. Well, not really. Again, this example was taken from the Cambridge Essentials textbook. The Venn diagram. So they've drawn a Venn diagram for me. Thank you very much. They've told me that there are 2 people who so 3 people in total for A, 7 people in total for B, 1 likes both A and B, and 3 don't like either A and B. Well, I don't know what those 3 are. Transfer the information from the Venn diagram into a two-way table. All right, so here's my two-way table. Now, the point about a two-way table is this. This is always A, and this is not A. You don't write A and B. You write A and not A, B and not B. So, the first one is the intersection, the overlap between A and B is 1. Thank you very much. The next one is not A, but B. So we're looking for everything that's in B not shared with A. That's that one there. So that's 6. What's the next one? So A and not B. So we want the one that's in A but not shared with B. Okay, that's that one there, which is 2. And then we want not A and not B. So that's everything outside of A and B, which gives me 3. So we have to now add these things together as a check. Now, I know a moment ago I said that adds to 1, but these aren't probabilities. These are numbers. So 1 plus 2 gives me 3. 6 plus 3 gives me 9. Now we add across. 1 plus 6 is 7. 2 plus 3 is 5. And now we do use something that we use in actually accountancy. We do it's called double check accounting. And what that means is we make sure that when we add down that row and across that column they add the... Try that one again. Down the column and across the row. I always get those the wrong way around. That they add to make the same thing. So does 7 plus 5 equal 12? And does 3 plus 9 equal 12? It does. And so I am happy with that information. All right. So this is a probability table or a Karnaugh map. I get confused about which one round it is, which is weird. So now it says to find N. What's this N business? Well, the great thing is it just means number of. If we were to write PR, A and B, then that would be asking us to find probabilities. But because we want to try and find N, it's just saying, well, read off the number that is in A and B. Which bit's in A and B? Well, I can either use the Venn diagram or I can use the two-way table. But as far as I'm concerned, N means intersection. That's the overlap. I'm just going to write down the number 1. The number in not A and B. The area that's not A and B. So it's just B on its own. Again, that's this area here, which is 6. A and not B. So I want the area that's in A but not B. All right, so that must be 2. God, I'm powering through this. The power of these tables. Not A and not B. That's what's not in any of them. Well, that must be 3 from that diagram there. Oh, what does this NA mean? again, how many are included in the whole of A? Well, that includes this 2 and this 1, which is 3. How many, I love this is so cool. How many are not in B? Oh, now this is a huge trick. The ones that are not in B are the ones that are here and here. So remember, when it's not in B, it's looking at those that are in just A and all the others as well. So in fact, in this situation, that would be 5. And so moving on to the number of A union B. Now remember, we've met union before, and that's where we have all of the things inside A and B added together. So A is 2, 1 and 6. So when I add 2, 1 and 6 together, what do I get? 6, 7, 8, 9. And so the number of elements inside A union B, or A or B, is 9. This stuff is great. All we're doing is adding numbers together. And we're going to move on to the idea of probabilities. And remember, I said probabilities are different because we're now going to end up with fractions. We're going to divide by total numbers of things. So we want the probability of A, N, B, A intersection B. Well, we know where that is. The intersection is the overlap and there's one number. But because we want a probability, we have to divide by the total number of elements. How do we work that out? Well, you add all the numbers together in that Venn diagram. So what do we have? We've got 2, 3, 9, 10, 11, 12. There are 12 elements in there. So I've got 1 in the intersection and 12 in total. This stuff is just, the probability of not A. Well, we've already dealt with the idea of not B, so now we've got not A. So that's everything that's not in A, which is 6 for the B, and these 3 outside. So many people forget the 3 outside. Please, please don't. And that's going to give me 9 on 12, which can be cancelled down to 3/4. And one more to go. The probability of A and not B. A and not B. Well, we've actually already worked out the number that are in A, not B, which gave me 2 over 12. And I can cancel down to just 1 over 6. This stuff does not get any more complicated. If you can transfer from a Venn diagram to a probability table or a Karnaugh map and vice versa, and you can read these things, I promise you, this stuff is freaking awesome. Now, pretty much that's the end of the lesson, ladies and gentlemen. There will be questions on this in exams and all sorts of stuff. It's a fodder. It gets a little bit more complicated, but not really much. My advice is understand how that diagram works. Now, I'm done. I've called it a day. Have you done me that honour of subscribing? That little doohickey in the corner? No. What about this big doohickey that's just here? Oh, come on, click it. Get out there. Put some stuff on Instagram and Facebook and do me that honour, please, of just spreading the word. If not, there's a video for you over there to watch as well if you want to. All right, I'm done. Thanks very much for your time. I'd look forward to seeing you next time. MaffsGuru out. Bye-bye.